Hi, I'm Mr. V, and today we're talking about illustrative mathematics, solid geometry, and this is lesson 3, creating cross sections by dilating. I'm going to start by talking about some of the homework questions from the previous unit where we were looking at slices of a solid. To begin with, select all figures for which there exists a direction such that all cross sections taken at that direction are congruent. And so if we have a triangular pyramid, I would draw that by drawing a triangle. And I'll draw a second triangle over here, kind of to the side. This one doesn't work. There's no way that you could do a cross section in the same direction. They would all be congruent. How about a square pyramid? Square pyramid will do the same thing. This time I'll draw a triangle. I'll draw my second triangle. I'm going to draw this piece like this. And this is the same thing. You can't do that. Now prisms, they have the same top and the same bottom. If I have a rectangular prism, one way to draw this is to draw a rectangle. And then I'm going to draw a second rectangle, part of it over here, and I'll connect these pieces. And you see that this is like a box or like a rectangle. And if I were to draw dotted lines from the stuff in the background, this is one way to draw it. And you can see if I slice it horizontally all the way across, this would be the same cross-section area. That's true for any prism, even if it's a, what do they call this? One that is not straight up and down, but it's slanted. And there's a name for that, and I forgot what the name of that is right now, but we'll be talking about that later on. A cube, that's another rectangular prism that works still. A cone would be more like these over here. So if I have my circle and my goes up to a point, even if you did this straight up and down, it's always going to be different. I think that this one might have two that are the same, but they're not all going to be the same in the same direction. So this would not work. A cylinder would. A cylinder is like a prism. It's not a prism, but it has a circular base, so it has the same top and bottom. And they call this, I can't remember what the name of that is. A sphere would not either. Imagine a cone lying on your desk. If you had a plane, vertical plane, not passing through the cone's uppermost point, so it would look something like this. Here I have a cone, and if I were to take it and do it vertically, so it would look, let me take this off, something like this. So it's not exactly a parabola, but it's going to be going straight up and down. It's not going to be exactly a parabola. It's not a triangle. It's going to have a curved top up here at the top. It's going to have a curve. So this would be, if I were to draw this, sketch it, looks something like this. It's going to be something like that. If it's a horizontal plane and it's a cone, can you see that's going to be a circle? That's going to be a circle. And the last piece of this, so this would be a horizontal plane, would be a circle anywhere along this cone, and a diagonal plane. And this is my last one here to show. You can see if I take this, I cut it at a diagonal, it's going to be an ellipse. These are called conic sections, and we will be discussing them later on in the course. But a diagonal plane would give you an ellipse. Two figures for which a circle can be a cross-section. Don't be bashful when you think about this. I want you to use your brain and seriously come up with it. One of them would be this figure. Do you remember what this is called? This is a cylinder. Could have this one. When I do this one and I cut it, a circle would be a cross-section. This would be a cone. And of course, a sphere would also give me a cross-section of a circle if I were to slice it anywhere across the cross-section. Doing the three-dimensional thing here again, if we do we echo this, notice this top part would be open, and the bottom part would also be open. I'm not sure what this would be, some type of, maybe some piece of glasswork that you could sell for a small fortune. We did the Objects of a rotation. What two-dimensional object would this be when you rotate it? It ends up being a cone, and of course that's going to be a triangle. When you rotate a triangle around the end, it ends up being rotating all the way around like this. I wanted you to match each one of these and not forget what it was that we learned. So we have SOHCAHTOA, and you might want to write that down. SOHCAHTOA, this is why we did this, so that we could select the correct ratio. And I noticed some people were struggling with this. Z is always going to be the hypotenuse, so I'll mark it here. But if A is my reference, this is the opposite and this is the adjacent. So the sine would be opposite, y over z. The cosine is x over z. The tangent is the opposite over the adjacent, which is y over x. If B is my reference angle, x is now the opposite. All the way across, this would be the opposite. This would be the adjacent. So the opposite over the hypotenuse would be x over z. The cosine would be y over z. And the tangent is x over y. In today's lesson, normally I would have you explore it and then we discuss it, but instead I'm going to show you today what it is that I want you to learn from this. If I have my original object, let's just say that this is my original object down here. And this would be a scale factor of 1. So if I took this object and I dilated it by a scale factor of 1, I'm at the same place where I started. My point of dilation is where the scale factor is 0. In between here, this is going to be between 0 and 1. So in between here, this might be scale factor of 1/2, scale factor of 3/4, a scale factor of 1/4. And the big idea for today's lesson is, first, my length of my starting length, if I dilate it by some scale factor, it's going to give me my ending length. And this is true if I'm getting bigger as well. So if I'm getting larger on this than smaller. The second part of this, which is what we're going to explore, is if I take an area of this piece and I want to get to the area of the second, I have to multiply by the scale factor squared. Now, let's talk about this. Let's go on down. First thing we did was we looked at trying to dilate this piece. You come up with what you think is what it is, and then you actually use the dilation tool. And what do you notice and what do you wonder? And we look at what the students noticed and wondered, and we came up with, oops, sorry. Here we go. Students. The sides of this figure. I need to move this thing out of the way. What is this? The sides of this figure look like they're twice as long. This is a scale. This is my original. This is where it's done. Notice I go twice as far from the point of dilation for each of these points because it's a scale factor of 2, getting larger. And this looks like it's twice as long. This dilation looks like a triangular pyramid. Yeah, it looks like a pyramid if I do all the dilations together. And the triangles look like cross sections of that pyramid. Is the dilation of the dilated triangle area this twice the area of the original? This is 1. This would be 2. Is this area twice as large? It's actually twice squared. So it's 2 squared, which would be 4 times as large. What would happen if we dilated the circle or a rectangle? And that's going to be something we'll do later on in the lesson. Finally, what if would it look like if we added another dilation with a scale factor, with a different scale factor to the same drawing? Say it was smaller than 1, for instance. What if it went smaller? And that's what we looked at here. We're getting smaller than 1. The figure is getting smaller. It could be getting larger if my scale factor is larger than 1. So if we were in the brick and mortar, if I was in there with you, we would probably build this mobile. And instead, I have these 3 GeoGebra applets to check out. The first one is one that you might want to do. If I have a horizontal, let me just make this. I have a horizontal plane, and you can see this. Here it is, horizontal. It's below my figure, and I can move it up, move up the plane. You can see what kind of figure it's going to be. Now, if I'm going to look at it viewed from the section, what this does is it makes the plane perpendicular to me. So you can see I have a rectangle. And if I'm going to go up about halfway, it's about halfway, you can see that the area of the length of this is supposed to be half of whatever this length is. But this area is 1/4. So instead of 0.5 being my dilation, when I do the area, it's going to be 0.5 squared, or 1/2 squared, which would be 1/4 the size of the original. That's something to notice. Also on this drawing, and this is a really interesting diagram for you to explore, and you really should. What if I tilted it? What if I tilted it, and what kind of figure is this going to be? Let's just look at the section. And can you see this might be an isosceles trapezoid? If I bring it down a little bit and rotate it, now I'm going to rotate it, and let's see what kind of figure this is. This is looking parallel to the plane. You see each one of these sides is different, and none of them are parallel. This would make this a trapezium. A trapezoid is when we're one pair of sides is parallel. Trapezium has no pair of sides parallel. And we can also rotate it more, and you could actually make this into a kite. I think you can make it into a kite, something like a kite. There's a lot of different things that you could get out of this by rotating this. And notice that this is cutting the pyramid at a slant. So different ways to explore. The second GeoGebra applet that we will look at is this one here. Now I've got this dilation, this original ABCD. I'm dilating it. Notice this is a length of 2. The blue is the length of 1. The blue, the original has an area of 4 blocks. This blue has an area of 1. So if its scale factor is 1/2, the area is 1/2 squared. It's going to be 1/4. You can see that this is true whether I'm at a flat level or whether I raise it up. And notice this is the middle level. So from F to E is 1, and to F to the blue is going to be half. So this is a scale factor of 1/2, and my area is going to be 1/4. This is the second one we explored. The third one, and this is one that I wanted you to explore, and this is where we take the original, and I didn't do this, but the original had this center point somewhere over here, like this. You can see it's going to be, if I were to move this around, this would be like in the center of this. We had to move this point E. You can click on it and move it up and down, click on it sideways, and we want it to move it towards right over the A. When I do that, this is going to be over one of the blocks, and this is one of the blocks. Now look, this polygon has an area of 1. My HG is the length of 1, and that's where this is in the plane, the scale factor. This is the length of 4. So this is 4, and I'm scaling it. I'm using a scale factor of 1/4. But the area is 1/16. This has an area of 16, and this is an area of 1. The area of this is 1/16 of the original. That's K squared. My scale factor, 1/4 squared. What if we move this down? You can take this and you can drag it. I can move it down. You see how this is now 2. This is 4. So my scale factor is 1/2. I've scaled it down by 1/2. And my new figure here has an area of 4, whereas the original was 16. That's 1/4. But my scale factor is 1/2. So the area is 1/4, which is 1/2 squared. That's kind of what we're looking at here. And of course, you can do this at 3/4. And at 3/4, it's really kind of weird. Why is this 9? Well, let's look at that for just a second here. I'm going to go back to my sketch here. If my scale factor is 3/4, and my original area was 16, so if I do 16 times 3/4 squared, what do I get? Well, 3/4 is the same as 9/16 when you square it, times 16, and this is equal to 9. So it's no wonder that this, when it's 3/4, my area is going to be 9 when the original was 16. So my original area is 16. When I do this by 3/4, 3 out of 4, my area is going to be 9. That's something to explore. There's some questions that you're supposed to answer on this. And first of all, one is to fill out this table where you see what the scale factor, how long is h could be, what's the area. And just thing I want you to notice is that the area is proportional to the scale factor k squared. That's the big idea. Some other questions. If you're in 3 dimensions, what does k equals 0 look like? And I pointed that out earlier. K equals 0 is the point of dilation. It is not a triangle. It is not any figure. It's just a point. It is the point of 0. It is not. So to be a dilation, it has to be greater than 0. And it would be less than 1. If it's equal to 1, then it's going to be congruence. If it's going to be a smaller one, it would be between 0 and 1. How's the area affected with changes to the cross-section? K squared. Is dilating by a scale factor of 0.9 and then dilating that image by a scale factor of 0.9 the same as dilating by 0.8? No, it would be 0.81. Be 0.9 and times 0.9. And some questions to ponder. Does the placement of the scale factor k equals 0.5 or half differ when you have 2 different pyramids that are the different heights? Yeah, it's going to be halfway. It's going to be halfway in their height. What is the difference between using a center of a rectangle that lies at the base of the center? That's the one that we did before, where it's either flat or it's collapsed. I'm still going to have the same dilation. The same figures are going to be dilated in the same way. What would happen if we dilated a rectangle by a scale factor of 0.1 or 0.9 using the vertex of the pyramid as the center of dilation? Well, it's either going to be really close to the base or really close to the vertex. So if it's 0.1, it would be really close to the vertex. 0.9 is almost 0.1, so it's almost at the base. And what is the range of scale factors between 0 and 1 when you're looking at the top of the pyramid being the vertex and the base being the bottom, being the 1? And if you had a circle one, what would this look like? So if I have my original circle, I have my point of dilation, I could have another circle here, have another circle here, like this. And each one of these is going to be extended along a dotted line. There is a summary for you to read, and then you can tell me about how you feel about what you learned today. Good luck and success.